Hi, today we're going to be going over A2 of the 2022 version of the Putnam. Now, I sat this Putnam myself, and this was a problem that I did on the actual Putnam. The problem says, for any integer n greater than or equal to 2, over all real degree n polynomials, let's say we choose one like p of x, what is the maximum number of negative coefficients in its square, p of x squared? I want an answer in terms of n. So, what that means is, for example, if I have degree 2, like I could have 1 plus x squared, and I take its square, it should only have positive coefficients. Or I could take 1 plus x minus x squared and square it. Some are going to be positive, some are going to be negative. The question asks, well, whatever you do get out, what is the maximum number of negative coefficients it can have? If you want to try this problem out yourself, you can pause the video and do so now. Now that I hope you've tried the problem out, I'm going to give my solution to it. This was the solution that I actually wrote down. First off, the answer is 2n minus 2. Maybe that's unexpected, maybe some of you guessed that right. If you did, give yourself a pat on the back. And if you want to try to prove this guess, maybe you can pause the video again and try to prove it if you didn't already do the problem on your own. But I'm going to go over my solution now. So first off, in these problems, it's kind of hard to guess what the right answer is. I don't see why it would be particularly obvious that 2n minus 2 is the answer. On the actual Putnam, for example, if you write out a polynomial of degree n, and it goes all the way up to an x to the n, and you square it, you realize that, okay, the constant term has to be a0 squared, then there's some stuff here, then there's some other stuff, and then x squared, and then the last term, which is x to the 2n, that one's going to be an squared. You notice that, okay, these terms are going to be positive anyways, and of course we've got 2n plus 1 coefficients here, so no matter what I do, 2n minus 1 is the maximum number of negative I can have. Like, it's an upper bound, not the exact maximum, but it's still like I cannot have more than 2n minus 1, right? Because 2 are always going to be positive. But is 2n minus 1 the maximum? Can I make all of these negative? Or can I only make all but one? Well, I gave you the answer already. I said it was 2n minus 2. And as it turns out, you can make all but the coefficient of x to the n negative. Let's do some examples now with some small cases to try to see what's happening and try to validate our guess. So first off, I did the most natural case, n equals 2. If you have a polynomial a0 plus a1x plus a2x squared, and you square it, well, what do you get back? For the constant, as we said before, it's just a0 squared. For the x term, well, you can have a1, well, actually, perhaps it's better to write it in brackets like these, because then you can really see how things multiply out better. How do you get an x term? Well, you could have a1x times a0 from here and a1x times a0 from here. There's two ways to get that, so you have 2a0 a1x. How can you get x squared? Well, you can have this times this, this times this, and this times this. Okay, and so there's for x squared, you've got 2a0 a2 plus a1 squared. Finally, for x cubed, well, you've only got this and this. Writing that out, that's 2a2 a1 x cubed, and then, as we know, for x to the 4, it's just a2 squared x to the 4. Alright, how negative can I make these? Well, let's suppose this coefficient is negative. What does that tell me? Well, that tells me that a0 and a1 have the opposite parity. Let's just say that this is parity 1. Well, it's even or odd, but I don't know what it is, but let's just say this is parity 1 and this is parity 2. Okay, I know that a0 and a1 are the opposite parity. Okay, what if the thing in the middle is negative as well? A0 times a2 plus a1 squared. Well, a1 squared is a positive number no matter what we do. For this to be negative, this has to be a negative number, but that means a0 and a2 are the opposite parity. But then that means that it's in the p2, because there's only two parities. That means it has the same parity as a1. Right, but then you look at this term, which is a2 times a1. These are the same parity terms multiplying together. This is going to be positive no matter what. Okay, so if we've actually got that these two are negative, then this one's forced to be positive. So you can only get up to 2 like this. Well, What if I said this one was negative, but then instead of the middle, it was this one that was also negative? Okay, well then that would tell me that A2 and A1 are the opposite parity, but then because A1 has the opposite parity of A2, that means A2 and A0 have the opposite parity. But then this thing is positive, because well, this is A2 times A0, which is positive because they have the same parity, and A1 squared is always positive. Okay, so it turns out no matter what configuration I do have, it always turns out that one thing is going to be forced to be positive. And I guess the last case left is suppose I started off with this being positive, then A1 and A2 have the opposite parity, and if this is positive again, A0 and A2 have the opposite. Sorry. Yeah, that would mean A0 and A2 have the opposite parity, but then that means A0 and A1 have the same parity, so this term is going to be positive. Okay, so I've sort of pretty much convinced myself, I've proven really that for this you can have at most two coefficients negative. You know, whichever two you choose two to be negative, the third one's going to be forced no matter what you picked. Okay, well, let's try another case. You know, because usually when you're doing these small cases, you want to do one that's even, one that's odd, maybe one that you think doesn't work out, you know, just for safety measures. This is the case of n equals 3. You have a1x, a2x squared, and it goes up to a3x cubed, and you want to square this, so I'll just write it again. It goes a2x squared plus a3x cubed. Okay, what is the well, first off, we don't really need to care about the constant coefficients, so I'm just going to not write that. But I'm going to write the coefficients of x squared, x cubed, x to the 4, x to the 5. And we don't really care about x to the 6 because we know that that's always positive. Okay, I have these 5 coefficients that, well, these are the ones that matter. For x, if you can notice actually, the only way I get x is the same thing as the only way that I got x in the case for n equals 2, right? Because, well, it's the same. I multiply these together, and everything higher power, it doesn't really matter because it's going to multiply to some power of x that's greater than 1. So it's the same thing actually. It's a0, a1 here as well, or rather 2a0, a1 here. And for x squared, it should be the same thing, 2a0, a1 plus 2a0, a2 plus a1 squared. Now for x cubed, things change because now I have a cubed term. Now things are a bit different for the x cubed case because, well, we still have the same coefficients here. This 2a2a1, it doesn't go away. I still have 2a2a1 because I can still get it. But now I can also get x cubed in another way. I get it by this, and I get it by this. And so I have a plus 2a3a1. Okay, what about x to the 4? Well, I have the same thing going on with, you know, I get a2 squared because I had a2 squared before. And I also now can get a3a1. And for x to the 5, I have 2a3a2. Okay, let's get back to doing the same analysis we did before. Let's say this is my two parities, plus or minus. I don't know what they are, but they're two parities. Let's say that this coefficient is negative. Okay, so a0 and a1 are the opposite parities. If this one's negative, then because a1 is a square, doesn't really matter what its parity is, it's always positive. This thing would have to be negative, but that means that a0 and a2 have the opposite parity, so a2 is here. Okay, let's sort of leave this out for now, and let's look at x to the 4. What if it was negative? And actually, I guess, let me give you the reason for leaving this out, perhaps. In most Putnam problems, like the maximum, like an upper bound, it's kind of easy to prove something is an upper bound. Like we showed that 2n minus 1 is an upper bound because, well, the first and last coefficient are always positive. And so for a long time, I did actually think myself, oh, 2n minus 1 is the maximum because, you know, you prove the upper bound easily, and then you want to, the hard part should just be constructing. And then I tried constructing, and I realized, wait a second, no matter how I do it, it wouldn't work out. So I figured out why wouldn't it work out, and the reason why it wouldn't work out was because, for example, let's say I had x to the 4 is also negative. Okay, a2 is the square, doesn't really matter. a3, a1, this has to be negative. That means a3 and a1 are in opposite parities. And so a3 is actually here. But now I go back to x cubed. I visit this again and I see, wait a second, a2, a1 are in the same parity, and a3 and a1 are in opposite parities. Actually, I made a mistake here. This should be a0. Oopsies. I probably even said a3 times a0 and then I just wrote a3, a1. Anyways, a3, a0 are also in the same parity by our analysis. And so this thing should actually be forced to be positive. We don't really even care now about x to the 5. We just know, okay, never mind. We actually can't really reach our, what we guessed to be our upper bound. And so at this point I kind of felt, well, damn, my guess was wrong. But then if you look at x to the 5, you see a3 and a2, well, these are opposite parity, so this thing is actually negative. So perhaps what's really happening here is that all the coefficients, except for the middle one, all but those you can make negative. And as it turns out, well, this was a guess, again, and I went up to the case of n equals 4, fourth degree polynomials, and I squared it out, yes I did, and I wrote out everything, and I did the same thing, and I saw, okay, I'm convinced now it works. And perhaps it's a good practice to do that, because 2 and 3 are small numbers, but now that we really know that this is the right answer, and you kind of can see how this is going to generalize. It's probably not a good use of our time to go over it, but maybe if you want to really convince yourself, it's good to do examples to guide your thought. Right, so let's get to proving it. First, note that there's actually two things to prove. There's two steps to this. Step 1 is to prove that 2n minus 1 is impossible. We know first off that 2n and 2n plus 1 are impossible because the constant and the x to the 2n terms are always positive. But now we also want to show that for all n, 2n minus 1 is impossible. Well, we did the case for n equals 2. We also did the case for n equals 3, as I just said above. Let's do it in generality. So let's say I have the coefficient of x squared, x cubed, and this goes all the way up to x to the n minus 1. And I have the coefficient of x to the n, I have the coefficient of x to the n plus 1, and I have the coefficient of x to the 2n minus 1. Okay, well, and my polynomial is a0 plus a1x plus a2x squared. This goes all the way up to an to the x, an times x to the n. Okay, the coefficient of x, well, it's always going to be 2a0, a1, no matter what the degree is. It actually doesn't really, if you increase the degree, you can see why it wouldn't change. Same thing here, like this thing would also always be 2a0, a2. Well, our degree is at least 2, so there always does exist in a2, and plus a1 squared. Okay, x cubed might be different for n equals 2 and n equals 3 because, well, in n equals 3 you have a3, whereas in n equals 2 you don't have a3. And so, you know, things might start looking a bit different there. In generality, if I have my coefficient k, the coefficient of x to the k is, you can sort of convince yourself why it's true, but it's just because of how brackets work out, is the sum over all ap times aq, where p plus q is equal to k, and p and q are both less than or equal to n. Well, this should be kind of obvious, I guess, because, well, there's one term here, let's say a p x to the p, and there's another x to aq x to the q, and these have to add up to k. That means their powers have to add up to k, and, well, you're summing over all such configurations. Okay, let's just say technically we did the case n equals 3 anyway, so we can assume n is greater than 3 strictly, and so I'd be able to write down this coefficient more explicitly. I can say it's a3 2a3 a0 plus 2a1 a2. I believe that's right. And for x to the n minus 1, well, it's something of this form. Ditto for x to the n, ditto for x to the n plus 1, where instead of this as being k, it's just replaced by what this power is. And for x to the 2n minus 1, well, it turns out to be pretty simple. All you really have is an and an minus 1. These are the only things that can add up to 2n minus 1, where, you know, these conditions are satisfied. Okay, so it looks like this. Now what I'm going to do is, I'm going to suppose all of these were positive, and I'm going to come in at a contradiction. Okay, well, suppose this is positive. Or sorry, oops, negative. I mean negative. So if I'm going to suppose all of these are negative, and I'm going to get a contradiction. Well, suppose this is negative, then a0 and a1 have to be opposite parity. And also, we don't have to worry about any being 0, because it's like, well, if it's 0, then it's 0, which is considered not negative. It's not considered positive, but it's also not negative, and I'm assuming they're negative, so they have to be opposite parity. Okay. I've got this. I suppose this is negative. What do I get? I get that a1 squared is positive, so a2 must be the opposite of a0, which we know this from before. It's the same thing going on. If this is negative as well, because a1 and a2 are the same, that means a3 and a0 are the opposite. Okay, it goes on like this. If I do it for x to the 4, I see I'd have to have a4 here. Why? Well, I'm gonna do it inductively. So I know that a0 is 1 parity, and a1, a2 all the way up to let's say ak minus 1 are the same parity. What can I say now about the parity of ak? Well, the first time ak comes is in the expansion of x to the k, right? In the expansion of x to the k, first it looks like 2ak a0, and then ak never appears, because, well, the only way to have p plus q equals k, where one of them is equal to k, is to have the other be 0. And we have that case right here. And well, this would be something like ak minus 1, a1, and blah blah blah. It would have other terms now. You'd have other terms like ap, aq, but none of these are going to be, all of these are going to be from here. So when these are going to multiply out, they're going to be positive, 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 positive. You want your whole thing to be negative, though. So that means this thing must be negative. Well, what does that mean then? That tells you that a0 and ak are the opposite parity. So ak goes in this place. Okay, so, well, by induction, I actually get to show that all the way up to an minus 1, if I consider up to n minus 1, these all have the same parity. Okay, that's interesting. And now, if I go to n plus 1, x to the n, if I look at the coefficient of x to the n plus 1, this is an interesting coefficient, right? Because we don't have an plus 1. So, well, the only way to get the coefficient of x to the n plus 1, it's going to have 2an a1 in its expansion. It's going to have 2an minus 1 a2, blah, blah, and it's just other sums of the form ap, aq, where both of these p and q are here. Well, if I want these to be negative, again, by the same argument, this is positive, blah, blah. These are all positive stuff. I want these to be negative. I want this to be negative. I want this thing to be negative. But, well, I know that this is positive. I know that this is positive because, well, these are all coming from here. Okay. But now for this thing to be negative, that means a1 and an are in the opposite parity. So now I actually get that an is here. An is in this p1 place. Okay, so, right, we sort of determined the parities of all of our coefficients now. We know that, okay, if I did have 2n minus 1 negative coefficients, or well, not even 2n minus 1, sorry. If I had that these and this are negative, which definitely if I have 2n minus 1 coefficients, I would have that. I would then get, well, that a0 and a1 are the same parity, and then a1 up to an minus 1 are the opposite parity. But now, actually, I want to investigate the coefficient of x to the n. I want to show something breaks. Well, this would be 2an a0, 2an minus 1 a1, and you know, other stuff where this is ap, aq. All these p and q are smaller than n, so they're in the same sort of parity section, and they multiply to positive stuff. An minus 1 and a1 are also in the same section, multiply to positive stuff. An and a0 are now in the same stuff, so they actually multiply to a positive number as well. And so actually it turns out that this thing is going to be positive. So it's actually impossible for the coefficient of x to the n to be negative, but we assumed it was if we had 2n minus 1 negative coefficients. Well, that's our contradiction then. It's quite literally impossible to have all of them be negative. The coefficient of x to the n cannot be negative if all of them are negative. That's a contradiction. So therefore, for every n, and of course this is n greater than 3, but, well, it doesn't really matter. We just showed it for n equals 3 and 2 as well. For every n, I have less than 2n minus 1 that are negative. Okay, once I proved this, I sort of started guessing maybe 2n minus 2 is the bound. Because, well, we had to do a bit of work to show that this is actually an upper bound, and there's two steps usually, so perhaps this is a reasonable upper bound, and well, I know it's a reasonable upper bound. I did the case for n equals 3. I got that there were 4 that you could make negative. I did the case for n equals 2. I got that there were 2 you can make negative. 2n minus 2 works out. The formula works out for a few numbers. Probably it's true. Of course, you shouldn't take that as a rule, but probably it's true. It's good to say that that's true for guesses, as long as you can prove it. Well, that's step 1, to show that 2n minus 2 is always a hard upper bound for all n. You can never get more than 2n minus 2. And now step 2 is to show you always can get 2n minus 2. Now, I know some people, after the exam, they gave an explicit construction, and if I wanted the video to be shorter, I could have just given their explicit construction. I could have just said, oh, let this be this stuff. I'm not going to do that. I'm going to give the way that I solved it, because I feel like I can provide better intuition as to why I thought of what I did think of, So perhaps that's more instructive, but actual construction, I think someone had a construction like 1 minus x squared, and then blah, 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 it goes up to like minus x to the n minus 1, and they just had plus n x to the n. If you squared this, you just prove that stuff works out. Okay, I don't really see, how someone would come up with it. Maybe, actually, it's not too hard to come up with it, but let me just go over how I did it. Well, it's the same thing here. I sort of just went, let me just make this negative without loss of generality. Well, actually, let me copy paste what I wrote down here for the coefficients. Right. So I have these coefficients, and I want to make all but x to the n negative. Okay, so I just want to focus on making this negative, and I want to focus on making the others negative. Okay, first off, if I want to make x negative, all I really need is a0 and a1 are opposite parity. Now I have to actually choose a parity. Okay, without loss of generality, let's just say a0 is the positive one and a1 is the negative one. So, okay, all I have to do is make a0 positive and a1 negative. Okay, which I can clearly do that. I'm going over all real polynomials here. To make this negative, well, I know that it must be true that a0 and a2 have the opposite parity, but I also need something more. Specifically, I need this inequality, right? a1 squared is less than 0. That's what it means for it to be negative, which if I solve around for, I get, well, it's an inequality. I can solve around for it, and I would get that 2a0, a2 is less than minus a1 squared. If a0 is not 0, I would have, this is, whatever the point of it is, I know that I have some inequality for a2 to satisfy, and, well, actually, if a0 was 0, then there's no way that this would be negative. So I would want a non-zero a0. That's why I would pick something positive. So yeah, never ignore what I said there. I picked something positive. 0 is not positive. So I know a2 has to satisfy this. Well, I'm going over all real numbers. This is I said a1 is negative, but it doesn't matter because its square is always positive, and this is a negative number. So I'm saying a2 has to be somewhat negative. It's less than some constant c, which I know I can figure it out. So I can always find this a2. So this a2 always exists. Okay. And so I can make this second coefficient. Perhaps I shouldn't have erased that. Yeah. I can make the second coefficient. Well, I can make it negative. Can I make the third one negative? Let's see. I have just an inequality 2a3 a0 plus 2a1 a2 is less than 0 to satisfy. If I just do some basic algebra, this is pretty much the same as me saying less than a1 a2 over a0. If I didn't mess that up. Note that a1 a2 are the same parities. So this is a positive number. I'm taking the negative of it. So again, this is just saying a3 is less than some negative number. I have all the real numbers in the world to choose from. I can always find something that's less than some fixed negative number. So a3 exists. And sort of going on in this way, I get that xk now, where k is less than n, is always, and supposing that I made all the other xk minus 1 coefficient, all the other coefficients negative, I would get that, okay, xk has this in its expansion, and it has like some ak minus 1, a1, and some other blah 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 stuff, and that's less than 0. And I need to now show that AK satisfies some inequality of like the sums of AP, AQ, all of this over 2A0. The thing is, these AP and Q, each P and Q is a number less than K, which means that they're in the same parity slot, and so they multiply to something positive. This is a positive number. I'm taking the negative of it. I'm saying it's less than some negative number. AK always exists. So, okay, AK minus 1 existing by the way we want it to, and actually all the numbers up to AK minus 1 existing by the way we want it to, implies AK exists. Okay, so I've sort of got an algorithm now. I just need to, like, at every step when I'm choosing my coefficient of x to the 4, that's the first time I have to choose a4, so I choose a4. And at x to the 5, that's the first time I have to choose a5, so I choose a5. Okay, something fishy happens now. I have to choose an now, because of course we just showed that we can make this negative, so we can just ignore it. When I want to make this negative, though, I have to choose an, right? That's the first time I have to choose an. But once I choose an, I can't really change it for this or this or this, right? Because well, there's only an. It only goes up to an. It's a degree n polynomial, so there's no like n plus 1 term when I'm expanding and taking the coefficient of x to the n plus 1. There's no like an plus 1 times a0. So once I determine an, it has to be when an such that I can make all of these negative. But going on the same sort of route, if I have the coefficient of x to the n plus k, it has the term 2an, ak plus some sum of ap, aq, where the p's and the q's are now both less than n, because this is a degree n polynomial, and that means that they're in the same parity slot. Okay, but now I have k is greater than 0, so something different happens here, because if I want this to now be less than 0, I say, okay, an is less than minus ap, aq over 2ak, right? Not exactly. Note that AK is a different parity. It's actually, by what we've chosen, it's negative. I'm dividing by a negative number. That's bad, because that flips the signs of inequalities. And that actually makes sense, right? Because if I said, oh, this is how it is, this term would be this term would be positive, because this is all same parity stuff multiplying and adding together, and this is negative. So you're saying an has to be negative, but that's clearly not what we want, right? We know that this is what the parity sort of should look like. That's because, well, ak is a negative number, because k is greater than 0, and we showed nk is less than n minus 1, or less than or equal to n minus 1. So the inequality sign flips when you multiply by a negative number. So it actually says this, okay, here. Yes. Well, or you can equivalently write this as ap, aq over ak. Minus, well, because this is a positive number, this is a negative number, negative is positive, so really what the point I'm trying to make is that this is a positive number, and it could be as big as you want it to be for x to the k, but note that there's k equations to satisfy, namely, let me move this down. Note that for xn plus k, the equations to satisfy would be, well, these are all p plus q such that it equals n plus k, and the p and the q are both less than or equal to n minus 1, because well, the n term is with us here. So this is for k in 1, k in 2, well, even actually 0 technically, but this is for k in 1, 2, n minus 1, and for k equals 0 we have the well, actually not k equals 0, sorry, just from 1 to n minus 1, because k equals 0 is not the case that we can make it negative, because that's x to the n. So we have it from 1 to n minus 1. We have n minus 1 equations like these. So we have, let's say, I would write it as like condition 1, an is bigger than this, which is an expression that I can completely determine in terms of my last n minus 1 coefficients. Condition 2, an is bigger than this, another condition that I can completely determine. Same thing goes on. I have n minus 1 conditions on my an. So I'm saying an has to be bigger than these n minus 1 positive numbers. Well, I can definitely do that. I have all the real polynomials in the world to choose from. I can make an any real number I want, and I can just make it extremely positive, and such that it satisfies all of these inequalities, and then I'm done because of my construction. I chose my an such that this is satisfied for all k, and you can work this out. You can work out an example. I had one written out for the case n equals 5 to see that, well, this is literally an algorithm. You can start off with a0, a1, and you can say, well, let's say a0 is 1 and a1 is minus 1, and then I would have an inequality for a2. I would have a2 is less than minus a1 squared over 2a0, which if you see is minus 1 over 2, but then that I can just use minus 1 because minus 1 is less than minus 1 over 2. Perhaps it's better to write it like this. This is a0 and this is a1, this is a2. I go to a3, a4, and I also want to pick a5, which would be here. Similarly, a3 has to satisfy some equation. It's namely the equation minus a2, a1 over a0. That says that it must be less than minus 1 strictly, so I can just take minus 2. Now again, a4 has to satisfy an equation, namely this. And I have already worked this out on a notebook next to me, so I'm just writing it off. But if you could see, this would turn out to be some number like 2 or something. And so I can just say a4 is equal to minus 3. That would satisfy this. And now I get to a5. a5 has 4 equations to satisfy. One is that a5 is bigger than 5. The other is that a5 is bigger than 6. And the other is that a5 is bigger than 9 over 4. And finally, a5 is bigger than 0. Okay, this is the condition that comes from saying x to the 9 is positive, which I guess, yeah, is the last x to the 2n minus 1 condition. All you really want is that an and an minus 1 are opposite parity. So you don't need, this doesn't actually give you some condition on how big an has to be, but it doesn't matter. Well, I clearly know of a real number that satisfies these 3 numbers. It's the number 7. a5 equals 7 satisfies this. So my polynomial a1 minus x squared minus 2x cubed minus 3x to the 4 plus 7x to the 5 should be a polynomial with all coefficients but x to the 5 and of course x to the 0 and x to the 10 negative. And I'm going to expand it out. I'm just kidding. Wolfram Alpha should expand it out, and it should be on the screen right now what it looks like, and hopefully I've done this right. Otherwise I have to re-record this, which I really don't want to. Anyways, that's been the solution for Putnam A2 this year. I thought it was a fair problem. It had a nice investigative nature to it. It wasn't really obvious to guess what it would be. My obvious, well, not obvious really, my initial guess was that 2n minus 1 is the answer, because a lot of the problems they're like, the upper bound is very trivial to prove, and then you just, the tough part is really constructing something that satisfies all this. But when I was going down this journey, I realized, well, it's actually impossible to do that. And at this point, I could have, you know, I was thinking of giving up on this problem because I wouldn't have guessed it right. And I just spotted that, well, once I make this negative, all the other, well, perhaps x to the 5 is a better thing to do. Once I make this negative, all the other stuff gets forced to be negative. Or, well, the parities work out. The only issue with parity comes in x cubed. And so then I spotted, well, I can actually construct 2n minus 2. And so I've shown, technically, with understanding why this doesn't work, I've shown less than or equal to 2n minus 2, and I can quickly see why 2n minus 2 would be possible. And yeah, that's how I did it. And the actual Putnam, I did the example of a 4th degree polynomial as well, and I showed that the answer was 6 for that. Perhaps that took too much time. I did spend like an hour and a half or maybe hour and 45 minutes on this problem, but I really liked it. I thought it was a simple proof. Well, not too complicated with its techniques, not too clever with its ideas. You just sort of investigate what happens and you write in terms of math what's happening and just figure some stuff out. See what's forced, see what isn't forced. Yeah, I thought it was a fair problem for the A2 difficulty. Anyways, I hope you enjoyed this problem as much as I did. It's a pretty cool problem. If you want to see more Putnam problems, I solved another as well. I solved the problem B1. I really like the problem A3, I believe. I'm not sure. I'm thinking of making videos on these. If you want me to make videos on more of the Putnam problems, you know, and how I would like think about them on the actual Putnam, what I actually try it and whatnot. If you think that that's a useful thing to see or hear, let me know in the comments below. I think it might be useful to understand how to think about some problems, especially if you're new to contest math. But let me know if you have other opinions in the comments below. Anyways, I hope you liked this video. If this is your first time seeing my channel, I make a lot of contest math problems usually, and I post some fun theorems sometimes. Consider subscribing.